After understanding the role of electrostatic force inside the atom, an important question naturally arises. If positively charged protons repel one another because like charges always repel, then why doesn't the atomic nucleus fly apart? According to electrostatic force, every proton inside the nucleus should push every other proton away. Since many nuclei contain dozens or even hundreds of protons packed into an incredibly tiny space, the repulsive force between them should be enormous. Yet, despite this powerful repulsion, atomic nuclei remain remarkably stable. The answer lies in another fundamental force of nature known as the strong nuclear force. This is the strongest of the four fundamental forces in the universe and is responsible for holding the nucleus together. The four fundamental forces of nature are the gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. Among these, the strong nuclear force is the most powerful. Although it acts only over an extremely short distance, it is much stronger than the electrostatic force at that range. This immense strength allows it to overcome the repulsive force between positively charged protons and keep the nucleus stable. The strong nuclear force acts between particles called nucleons. The term nucleons refers to the particles found inside the atomic nucleus, namely protons and neutrons. Therefore, the strong nuclear force acts between proton-proton, proton-neutron, and neutron-neutron pairs. Unlike electrostatic force, which acts only between charged particles, the strong nuclear force acts on both charged protons and electrically neutral neutrons, because it depends on the internal structure of these particles rather than their electric charge. To understand why this force is necessary, imagine a nucleus containing several protons. Every proton carries a positive electric charge. According to Coulomb's law, each proton repels every other proton. Since the protons are extremely close together, only about 1 femtometer apart, the electrostatic repulsion between them is incredibly strong. If no other force existed, the protons would immediately push one another apart, causing the nucleus to disintegrate. Stable atoms would be impossible, and matter as we know it could not exist. Fortunately, nature provides a much stronger attractive force inside the nucleus. The strong nuclear force acts like an extremely powerful glue that binds nucleons together. Whenever two nucleons come very close to each other, this force becomes enormously strong and pulls them together. At these tiny distances, the attractive strong nuclear force is much stronger than the electrostatic repulsion between protons. As a result, the nucleus remains tightly bound despite the repulsive electric forces acting inside it. An important characteristic of the strong nuclear force is that it acts only over extremely short distances. Its effective range is approximately 1 to 3 femtometers, which is about the size of an atomic nucleus. Beyond this tiny distance, the force decreases very rapidly and becomes almost zero. This is why the strong nuclear force affects only particles inside the nucleus and has no influence on electrons orbiting far outside the nucleus. Because the strong nuclear force acts only at extremely short distances, nucleons must be very close together for it to operate effectively. Inside the nucleus, protons and neutrons are packed closely enough that the strong force binds them into a stable structure. Electrons, however, are located much farther away in electron orbitals, so they are not affected by the strong nuclear force. Instead, electrons are held around the nucleus by the electrostatic attraction between their negative charges and the positive charge of the nucleus. One of the fascinating aspects of the strong nuclear force is that it acts equally between different combinations of nucleons. It binds proton to proton, proton to neutron, and neutron to neutron. Although neutrons carry no electric charge, they play an extremely important role in nuclear stability. They contribute to the attractive strong nuclear force without adding any electrostatic repulsion because they are electrically neutral. This explains why neutrons are essential in many atomic nuclei. Consider the simplest nucleus, hydrogen 1, which contains only one proton. Since there is only one proton, no proton-proton repulsion exists, so a neutron is unnecessary. However, larger nuclei contain many protons that strongly repel one another. Additional neutrons increase the attractive strong nuclear force without increasing the electrostatic repulsion. In this way, neutrons act as nuclear stabilizers, helping to hold the nucleus together. For example, the nucleus of helium-4 contains 2 protons and 2 neutrons. The 2 protons repel each other electrically, but both protons and neutrons are held together by the strong nuclear force, making helium-4 an extremely stable nucleus. Similarly, the carbon-12 nucleus contains 6 protons and 6 neutrons, while oxygen-16 contains 8 protons and 8 neutrons. In each case, the strong nuclear force overcomes the electrostatic repulsion and maintains nuclear stability. As atomic nuclei become larger, the number of protons increases, causing stronger electrostatic repulsion. To compensate, additional neutrons are needed to provide extra strong nuclear attraction. This is why heavier elements usually contain significantly more neutrons than protons. For example, uranium-238 contains 92 protons and 146 neutrons. The large number of neutrons helps offset the enormous repulsive forces among the many protons. However, even the strong nuclear force has its limits. In extremely large nuclei, the electrostatic repulsion between protons becomes so great that the strong nuclear force can no longer hold the nucleus together perfectly. Such nuclei become radioactive and eventually undergo radioactive decay. During radioactive decay, unstable nuclei emit particles or energy in order to achieve a more stable configuration. This explains why many very heavy elements, such as uranium and plutonium, are naturally radioactive. The strong nuclear force originates from an even deeper level of matter. Modern particle physics tells us that protons and neutrons themselves are made of smaller particles called quarks. Quarks are held together by the fundamental strong interaction, which is carried by particles called gluons. Gluons continuously exchange between quarks, binding them together inside protons and neutrons. The force that binds protons and neutrons inside the nucleus is actually a residual effect of this deeper strong interaction. Thus, the same fundamental force that holds quarks together also indirectly holds atomic nuclei together. The strong nuclear force is vastly stronger than the electrostatic force at nuclear distances. Although it acts over a much shorter range, its strength is sufficient to dominate inside the nucleus. This balance between the attractive strong nuclear force and the repulsive electrostatic force determines whether a nucleus is stable or unstable. The importance of the strong nuclear force extends far beyond atomic structure. It is responsible for the enormous amounts of energy released during nuclear fission and nuclear fusion. In nuclear fission, heavy nuclei such as uranium split into smaller nuclei, releasing energy because the rearrangement of nucleons results in a more stable configuration. In nuclear fusion, light nuclei such as hydrogen combine to form heavier nuclei, also releasing tremendous amounts of energy. Fusion powers the sun and all other stars, while fission is used in nuclear power plants to generate electricity. Without the strong nuclear force, neither nuclear fission nor nuclear fusion would be possible. More importantly, atomic nuclei themselves could not exist. Every nucleus would immediately break apart as the positively charged protons repelled one another. Since nuclei contain nearly all the mass of atoms, stable atoms would never form. Without stable atoms, molecules, planets, stars, living organisms, and the entire universe as we know it would be impossible. It is also useful to compare the electrostatic force and the strong nuclear force. The electrostatic force acts between electrically charged particles. It can either attract or repel depending on the charges involved. Opposite charges attract, while like charges repel. It operates over relatively long distances and is responsible for holding electrons around the nucleus. In contrast, the strong nuclear force acts only between nucleons inside the nucleus. It is always attractive at nuclear distances and is responsible for binding the nucleus together despite the electrostatic repulsion between protons. To summarize the behavior of the strong nuclear force, it is the strongest of the four fundamental forces of nature. It acts between nucleons, protons, and neutrons. It binds proton-proton, proton-neutron, and neutron-neutron pairs. It acts only over extremely short distances of about 1-3 femtometers. It overcomes the electrostatic repulsion between positively charged protons. It provides stability to the atomic nucleus. Without it, atomic nuclei would immediately break apart. In summary, the strong nuclear force is the powerful attractive force that holds the nucleus together. It overcomes the intense electrostatic repulsion between protons, binds nucleons into stable nuclei, enables the existence of atoms, powers nuclear reactions inside stars, and ultimately makes all matter in the universe possible. Although it acts only across incredibly tiny distances, its strength is unmatched among the fundamental forces of nature, making it one of the most essential forces governing the structure of the universe. After understanding the structure of the atom, atomic number, mass number, and the role of protons, neutrons, and electrons, we can now explore an important concept known as isotopes. The discovery of isotopes solved one of the biggest puzzles in atomic theory. Early scientists believed that all atoms of a particular element were exactly identical. However, careful experiments showed that atoms of the same element can sometimes have different masses while still behaving chemically as the same element. This observation led to the discovery of isotopes, which are now one of the most important concepts in chemistry, nuclear physics, medicine, archaeology, and many other scientific fields. An isotope is an atom of an element that has the same number of protons but a different number of neutrons. Since the number of protons determines the identity of an element, all isotopes of a particular element belong to the same element. However, because the number of neutrons differs, their mass numbers are also different. To fully understand isotopes, remember that every atom is characterized by two important numbers: the atomic number and the mass number. The atomic number represents the number of protons in the nucleus, while the mass number is the total number of protons and neutrons. Since isotopes have the same number of protons but different numbers of neutrons, their atomic number remains the same, but their mass number changes. For example, every carbon atom has 6 protons. This is why every carbon atom has an atomic number of 6. However, not every carbon atom has the same number of neutrons. Some carbon atoms contain 6 neutrons, some contain 7 neutrons, and others contain 8 neutrons. These different forms are known as carbon-12, carbon-13, and carbon-14. Let us examine these carbon isotopes in detail. Carbon-12 contains 6 protons, 6 neutrons, and 6 electrons in a neutral atom. Its mass number is calculated by adding the protons and neutrons, mass number GeC, 6 plus 6 stoke 12, therefore, this isotope is called carbon-12. Carbon-13 also contains 6 protons and 6 electrons, but it has 7 neutrons instead of 6. Therefore, mass number DEC 6 plus 7 calc 13, this isotope is called carbon-13. Carbon-14 still contains 6 protons and 6 electrons, but it contains 8 neutrons. Mass number 6 plus 8 calc 14, therefore, its mass number is 14, and it is called carbon-14. Notice something very important. In all 3 isotopes, the number of protons remains exactly the same. Therefore, all 3 are carbon atoms. Only the number of neutrons changes, causing the mass number to change. Hydrogen provides another excellent example of isotopes. Hydrogen is the simplest element because every hydrogen atom contains only 1 proton. However, hydrogen exists naturally in 3 different isotopic forms. The first isotope is called protium, or hydrogen-1. It contains 1 proton, 0 neutrons, and 1 electron. Since its nucleus contains only one proton, its mass number is mass number Gek1 plus 0 Gek1. Approximately 99.98% of all hydrogen found in nature is protium. The second isotope is deuterium, also known as hydrogen-2. It contains one proton, one neutron, and one electron. Mass number Gek1 plus 1 Gek2 because it contains an additional neutron. Deuterium is heavier than ordinary hydrogen. Water containing deuterium is called heavy water, which is used as a moderator in some nuclear reactors. The third isotope is tritium, or hydrogen-3. It contains one proton, two neutrons, and one electron. Mass number Gek1 plus 2 Coke3. Tritium is radioactive and gradually undergoes radioactive decay. It is used in scientific research, self-illuminating devices, and fusion research. These examples clearly show that isotopes have identical numbers of protons but different numbers of neutrons. One of the most important characteristics of isotopes is that they have the same chemical properties. Chemical behavior depends mainly on the number and arrangement of electrons. Since isotopes of the same element have the same number of protons, neutral atoms also contain the same number of electrons. Therefore, their electron configurations are identical. For example, carbon-12, carbon-13, and carbon-14 each contain 6 electrons. Their electron configuration is 2.4 because their electron configurations are identical. They all form the same types of chemical bonds and participate in the same chemical reactions. However, although isotopes have nearly identical chemical properties, they have different physical properties because their masses differ. Heavier isotopes usually move more slowly, diffuse more slowly, and often have slightly different melting points, boiling points, and densities. Another important feature of isotopes is that some are stable while others are radioactive. Stable isotopes remain unchanged indefinitely. Radioactive isotopes, on the other hand, possess unstable nuclei that spontaneously emit radiation in order to become more stable. For example, carbon-12 and carbon-13 are stable isotopes. However, carbon-14 is radioactive. Over time, carbon-14 undergoes radioactive decay by emitting beta particles and eventually transforms into nitrogen-14. The radioactive decay of carbon-14 has an extremely important application known as radiocarbon dating. Living organisms continuously absorb carbon from the atmosphere, including a small amount of carbon-14. After the organism dies, it no longer absorbs carbon, and the carbon-14 already present begins to decay. By measuring the remaining amount of carbon-14, scientists can estimate the age of ancient fossils, bones, wooden objects, cloth, paper, and archaeological artifacts up to about 50,000 years old. Radioactive isotopes have many other important applications. In medicine, isotopes such as technetium-99 are used to diagnose diseases through medical imaging. Iodine-131 is used to treat thyroid disorders. Cobalt-60 is widely used in cancer radiotherapy because it emits powerful gamma rays that destroy cancer cells. In agriculture, radioactive isotopes help scientists develop improved crop varieties, study fertilizer absorption, and control insect populations. In industry, isotopes are used to detect leaks in underground pipelines, measure material thickness, inspect welds, and monitor industrial processes. In scientific research, isotopes serve as tracers that allow researchers to follow chemical and biological reactions. It is important to distinguish isotopes from ions, because students often confuse these concepts. Isotopes differ in the number of neutrons while having the same number of protons. Ions, on the other hand, differ in the number of electrons while the number of protons remains unchanged. Changing the number of neutrons creates an isotopy, but does not change the electrical charge of the atom. Changing the number of electrons creates an ion and changes the electrical charge, but does not change the identity of the element. For example, carbon-12 and carbon-14 are isotopes because they have different numbers of neutrons. Sodium and sodium ion are not isotopes, they are an atom and an ion because they differ in the number of electrons rather than neutrons. Another important point concerns average atomic mass. The atomic masses listed on the periodic table are usually not whole numbers. For example, the atomic mass of chlorine is approximately 3545 AMU rather than exactly 35 or 36. This happens because naturally occurring chlorine consists of two main isotopes, chlorine-35 and chlorine-37. About 75.8% of natural chlorine atoms are chlorine-35, while about 24.2% are chlorine-37. The value shown on the periodic table is the weighted average of these naturally occurring isotopes. Most elements found in nature exist as mixtures of isotopes. Therefore, the atomic masses listed on the periodic table are average values rather than the exact mass of a single atom. Scientists represent isotopes using standard nuclear notation. The mass number is written as a superscript, while the atomic number is written as a subscript beside the chemical symbol. For example, C represents carbon-12, C represents carbon-13, C represents carbon-14. In each case, the atomic number remains 6, while only the mass number changes because the neutron count changes. To summarize the important characteristics of isotopes, they have the same atomic number because they contain the same number of protons. They have different numbers of neutrons. They have different mass numbers. They have almost identical chemical properties because their electron configurations are the same. They have slightly different physical properties because their masses differ. Some isotopes are stable, while others are radioactive. The relationship between protons, neutrons, and isotopes can be remembered very easily. Same number of protons, same element. Different number of neutrons, different isotopes. Different mass numbers, different atomic masses. In summary, isotopes are different forms of the same element that contain the same number of protons but different numbers of neutrons. The identity of the element never changes because the atomic number remains constant. However, the mass number changes because the neutron count changes. Isotopes play an essential role in modern science and technology, from determining the age of ancient civilizations through radiocarbon dating to diagnosing diseases, treating cancer, generating nuclear energy, improving agriculture, conducting scientific research, and understanding the structure of matter itself. They beautifully demonstrate that atoms of the same element can have different masses while still retaining nearly identical chemical behavior, making isotopes one of the most fascinating and useful concepts in chemistry.